So hello again everyone. Today we will check how to solve exercise called lowest common ancestor of a binary tree. And the condition says that we will need to design a method that finds the lowest common ancestor of two given nodes in a binary tree such that the lowest common ancestor is defined between two nodes P and Q as the lowest node in T that has both P and Q as descendants, where we allow a node to be a descendant of itself. So we will need to create a method which will be called, for example, lowest common ancestor, and we will give to this method two arguments, root of our tree, P and Q. And below I have an example, so let's imagine that P is equal to 5 and Q is equal to 8, and their common ancestor in that case will be 2. Or let's imagine that P is equal to 7 and Q is equal to 4, and in that case their common ancestor will be 4. So I hope it's a little bit clear for you the idea of this task. So let me show you a visualization of algorithm which we will implement. So in that case we have this tree, and our P is equal to 5 and Q is equal to 2. And that case we will use depth first search, which means that for the implementation we will use recursion, and we will start from the beginning. We will go to the left, we will go to the left, and we will if we will not find any of our elements which we are searching, if we will not find P or Q, we will reach the end of this tree, which will mean that we haven't found any of the elements, for example in that subtree, because we reached the end. And it will mean that we need to stop recursion and go back to the root. Actually we will go back to the 6, then we'll search here, and so on and so on. I will show you right now the example. But in our case we will reach to this element 5, which is our P, and we will return back to the root. We will not proceed, we will not go to search the next elements, because when we call our method lowest common ancestor, we P and Q should be in that case, in that station, we suppose that P and Q are present in this tree. We just want to know their ancestor. And if we have found this element 5, it doesn't make any sense to proceed and to search in the depth of this tree, because the result always will be the same. Even if we will find this element here, it will mean that it's present. We have done some additional operations, but their common ancestor always will be 5. So because of that, we just find this element, and that's it. We go back to the root and start to search if Q is present in that subtree. And in the end, it will return null because 2 is not in that subtree, is present in that subtree, and the result will be 5. But in the case, if for example 2 is not present here, we return 5 here. We start to search in that subtree if 2 is present here. For example, instead of 0 we would have here 2, but instead of 2 here we would have 0. We would search here in that subtree, we would find this 2, we will go back to the root, and we will see that, okay, in the left side we have 5, okay, it's equal to our P. In the right side we have found 2, it's equal to our Q, so their common ancestor is equal to 3. So let me show you how it works more dynamically. So we start from 3, we go to the left subtree, which is this one, And we actually found our P here. We don't proceed, we don't continue to search in that subtree or in that subtree. We just return back to our root and start to search in that subtree. So we go to that subtree and we will go to the left. We'll start to search there. We'll go to the left and we will get null, which means that we have reached the end of that subtree. We'll go back to the root. We will go and we will search on the right side. There we'll have the same situation. We will reach the null. And actually in the end, because we don't have 2 in that subtree, when we will go back to our main root, we will return null because we haven't found 2 in that subtree. And here we will have null, here we will have 5, and we will need to put a condition. So if left is not equal to null, but right is equal to null, then in that case we need to return the root of the left, the result from the left which we have found. But if, for example, if right is not equal to null and left is not equal to null, which means that we have found the result also in the left side and also in the right side, then we will need to return their common root. So that's the main idea, and now let's proceed and to check the implementation for that algorithm, and I hope it will become a little bit more clear for you what's the idea and how the solution should be implemented. So let's start the implementation. Here I've already prepared the structure for the tree node and the signature of our method. Here we have 3 arguments, root of our node, of our tree, P and Q. Because we will use here recursion, first of all, like always, we need to think about which condition will stop our recursion. And our recursion will stop in the case if we haven't found any solution in the subtree, or in the case if we have found this solution. So let's put this condition. So here we will put root. If root is equal to null, or if root is equal to Q, or let's say P, and if root is equal to Q, then in that case we will return root. Okay, cool. Now let's call recursively this method for the left subtree and the right subtree. So let's do that. Lowest common ancestor. Here we will call it for the left subtree. And the right subtree. I'll just copy this, and here we'll change to right. Okay, and we will need somewhere to store the solution, the result. So let's do that. Let's declare 2 variables, left and right. Perfect. And now we can have 2 situations. We can have a situation when we have found the solution in the right and in the left subtrees of our root. In that case, we need to return their root, so where recursion have started. Yes, so for example, if we have root 3 and in the left side we have 2 and in the right side we have 1, where p is equal to 2 and q is equal to 1, then in that case the common ancestor will be 3, yeah, and we will need to return this 3. So, but it will happen only in the case if result from the left side is not equal to null, and if the result from the right also is not equal to null. And in that case, we will return null, or we will return root. But like in our example, in our previous example, we also can have a situation when we don't find the solution in the right subtree, but the solution is just in our left subtree. In that case, we need to make a check. So if, or maybe I will write something like that, if left is not equal to null, then in that case we'll return left. But if left is equal to null, it means that the right side is not equal to null, then we'll return right. So in that case, if you remember our previous example, we'll return just left, because right will be equal to null. Why it will be equal to null? Because if for example they both would not be equal to null, yeah, and left and right, then we just will return null. But if this will not work, yeah, it will not work only in the case if one of them is not equal to null. And if it's not equal to null, then we need to understand what side is not equal to null, and that's why we need this this condition. And we will just return the left node, and this one will be our solution. So that's the idea of that task and how it could be solved. And now let's check the complexity of that solution. So the complexity will be ON. It is time complexity, and space complexity is OH. So that's the solution. I hope it was clear, and we will see you in the next video. Bye.